Routing and switching. I mean, just saying it brings a smile to my face because there's so much a demand for people who understand routing and switching in computer networks today. We're going to, in this nugget together, you and I, we're going to demystify some of the magic, or what seems like magic to many people, regarding how does a network or how does a router determine where all these networks are that it needs to forward packets to, and how does a switch make its forwarding decisions, and what does it mean when people say VLAN or trunking? We're going to cover all those terms and more as we together go into the details of routing and switching. In this nugget, we get to reinforce what we've learned about the OSI reference model and the basics of networking and take a look at the world of layer 3 with exactly how routers do what they do. For example, how does a router know what to do with a packet when he gets it? How does he know where the remote network is? Well, that question and more are going to be answered by this nugget. We'll also take a look at what happens at layer 2 in the OSI reference model with switches. We've already had an introduction to that. We're going to cover some more advanced topics, such as spanning tree protocol and VLANs and trunking and how those terms that you're going to hear all the time, what exactly they are and how they fit in. We'll cover that as well. And then there's a little grab bag at the end. Now I call it a grab bag because in the objectives from CompTIA in section 1.4, there's a couple little pieces that don't exactly fit into routing or switching, and so we'll include those as well to make it a nice, well-rounded package. I'm super excited to share this information directly with you, so let's get started. So what exactly is routing all about? Well, that's a really good question. I'm glad you're here with me, and we're going to talk about it together. Before we get into these hockey pucks, which we know are the icons for a router, let's talk about something that we are very familiar with, and that is a house. So let's pretend that's the house where you live. Could be an apartment, a condo, doesn't really matter. And let's say it's connected with a sidewalk or a driveway to a street. We'll draw a beautiful street right there. And let's give it a name too. We'll call it Elm Street. So that is Elm Street. And if we ask the person at this house, hey, do you know how to get to Elm Street? What would that person say? I'll draw a little figure there. That person would say, of course I know how to get to Elm Street. I'm directly connected to it. And that's pretty obvious. So if somebody asked this guy how to get to Elm Street, he'd say, it's right out my front door. There's Elm Street. Just in that same light, a router knows how to reach different networks based on directly connected interfaces. So I'm putting a little blue, aqua, whatever color you want to call that, dot next to each of the router interfaces. And every time you see a router interface, that interface is connected to a different network. So R1 knows how to reach, it knows where it is, the 10.1.0 network, because it is what? It's directly connected. Are you with me? It's directly connected. So it knows how to reach 10.1, it knows how to reach 10.12 because it's directly connected. But all by itself, a router doesn't know how to reach this one, R1, doesn't know how to reach the 10.2 network or the 172.16.1 network or the 24 network or the 34 network because it's not directly connected. So unless we give them some additional information, R1 is going to do a terrible job of forwarding packets to those other networks that are not locally connected or directly connected. So when we talk about routing, routing really involves two things. Number one, it involves learning. What do you mean, Keith, learning? The router has to learn where a network is. So with directly connected networks, that's one way of learning. We can be directly connected. And there's only one other option, really. And the other option is somebody can tell you. You can be told. So, for example, as an administrator, we could tell this router, hey, dear Mr. Router, to get to the 172.16 network, 172.16.1 network, go ahead and forward it to R2. And because R2 is connected, he knows how to get there. So we could manually tell a router how to get to a certain network, or we can also go ahead and they call that a static route. I'll show you each of these. And the other option is dynamic. And that's all about learning. So our first piece here, routing. The first piece involves learning where the networks are. And as a quick reminder, the options are not very many. We can be directly connected, as in the case of R1, it's directly connected to these two networks. The R3 is directly connected to 3 networks, so it knows how to reach those. We can be told where networks are by using something called a static route, which is just information. So we could go to R3 and say, hey, dear Mr. R3, if you want to learn how to forward packets, or if you need to ever send a packet to the 1010 network, you go ahead and you forward it over to R2. And then also R2 would have to be told how to forward it. But if we manually, us, you and me, we configure these static routes, that's one way of training the routers. The other option, which is a lot easier, is called dynamic. With dynamic routing, we simply tell all the routers to take what they know and share it with everybody else. With dynamic routing, R1, because he knows about the 10.1 network and the 10.12 network, he'll share what he knows with R2. Now, R2 already knows about the directly connected network here, but he didn't know about 10.1. So with dynamic routing, R2 would be trained dynamically by R1. R1 would basically say, hey, if you ever need to connect to 10.1.0, I know how to get there. Go ahead and forward those packets my direction, and I'll take care of it. And that's it as far as the first step of routing is learning. So when somebody talks about routing on a network, they could be absolutely talking about learning about where the networks are. The second step of routing is actually doing it, meaning forwarding packets. The two-step process. And it's done in the right order. You learn where the networks are, the routers do, and then when they get a packet, they forward it. And a packet comes in, the router looks at something called its routing table. That means what it's learned through one of these options, and then it makes a forwarding decision towards the final destination. And usually that involves another router in the path, who then forwards it to another router, who then forwards it to the final destination. So that's it. That's what routing is all about. It's about learning where the networks are, and then secondly, making forwarding decisions to those networks. So let's take a look at these routers and what they know before we train them with any additional network information. So this is R1 in our diagram up here, and this is a command line interface, also sometimes called a CLI, to a network router. Now, a network router could be made by one of various vendors. We have Cisco, which is a pretty large vendor, and we have other companies like Juniper and other vendors like HP, and a lot of different companies make routers. So the actual commands may vary and will vary slightly between vendors, but the concept is the same, and that is, in this case, IP routing. So if we take a look at R1, on a Cisco box at the command line interface, which is where we are, I'm going to do a show IP route. And what that says is, please show me all the routes that you know about, Mr. Router, for IP, specifically IP version 4. So the output here, there's a lot of information up here. This is like a Dick Tracy decoder ring with a lot of details, but it's really quite simple if we look at the basic elements. This is saying how the routes were learned, and we talked about 2 things regarding routing. One is learning, and these are all the different methods that we could learn a route, including directly connected. And if we look down here, see the C right here? That C equates to those C's right there, which means that we have 2 networks. We've got the 10.12 and the 10.1, and we know about both of those because we are we're directly connected. Now, one other thing that we can notice here is that it subcategorized them, these 2 individual routes, under this one. And the reason it did that is because the 10 is a Class A address. I'm not using the standard default mask. If you go back to our IP section, I'm not using the standard default mask for a Class A, which is 8 bits, and that's why it put the 2 independent subnetworks that fall into the 10 category, the 10 network space, underneath it. Just describing why it did what it did. So what is this output giving us? Well, let's take a look real quick. This output, if we just clear this off for a moment, this output shows us a couple things. It says that if I need to reach the 10.12.0 network, I can forward packets out the interface fast Ethernet 1/1. If we look at our diagram, here's fast Ethernet 1/1, and here's the 10.12.0024 network, just as described right there. The other route we have is the route to the network 10.1.0, and that's this network runner here. And how did we learn those? We learn them because we are directly connected to them. But unfortunately, right now we have, and this is we have our PCs out here and our customers and our printers all connected. That's why I put the switch there to imply that we have other devices connecting through us. So the way this would work is this. You have a happy user. There's a happy user sitting right there at this PC. If they sent a packet that was destined, let's say to 192.168.0.17, so the packet comes into the router. Here's what the router does. The router looks at its routing table and says, okay, you need to send, this packet needs to be forwarded. In fact, let's take a look at the whole details of this. When the bits come into the router is going to look at those bits. And first of all, at layer 2, it's going to look at the frames and say, is this frame for me? And hopefully this PC would format the frame at layer 2 correctly for the layer 2 address of R1. Then if it is the layer 2 address of R1, R1 would continue to de-encapsulate it till he looks at layer 3, and the layer 3 packet would say 192.168.0.17, and at that point, the router would say, oh, that's not me, but I am a router. Let me see if I can forward that for you. Now, in this case, unfortunately, there's no information in the routing table that tells R1 what to do with this packet. And as a result, this packet destined from this PC here and going over to this device here, it's going to be dropped at R1 because R1 has no clue on how to forward a packet outside of 10.12 and 10.1. So that's the whole concept of routing, is looking at a packet, routers, looking at a packet at layer 3, looking at the IP address. If it isn't their own IP address, meaning the packet's not for them, they would make a routing decision based on what they know and how they can forward. So let's take a look at static options and making this a little bit better, a little better picture. Because the router doesn't currently know how to make a forwarding decision out to the 192.168 network, let's train him. And this is an example of a static route. So I don't want you to worry about the syntax, the actual commands on an iOS router. The iOS is the operating system on a Cisco router. The Internetwork Operating System, that's what iOS stands for. I know iOS also is the name of the operating system on like iPhones and iPads and so forth, and someone paid a royalty to somebody else to borrow that. So Cisco has been using the iOS name for decades. In any event, what we're doing is we're configuring the iOS. We're going to configure a static route. I just went into something called configuration mode. It's where you go in to configure things on a Cisco router. And to create a static route, we say IP route, and to get to the 192.168.0.0 network, and then it says, okay, well, how much of that information you just put in there, how much is the network and how much is not the network? I mean, which part is the network address space? And then we put the mask in. So this is the mask in decimal. If you haven't been through the section on IP addressing, I strongly recommend you go look at that first so you can appreciate this. And then after we say, dear Mr. Router, if you need to get to 192.168.0.0 with this 3-octet mask, meaning the first 3 octets are the network, if you need to forward to that network, here's what you should do. You should forward it to 10.12.0.2. Now that happens to be the IP address of R2. So we're basically playing hot potato. So we're telling R1, if you get a packet that's destined for this network, you don't have to worry about the rest of the world. You just hand it over to the IP address of R2, which we'll do right now. So R2's address, which I happen to know, is 10.12.0.2. Now, how did I know that? Well, the reason I know that is because I configured the network earlier. We could also look at that router. Now, if we do a show IP route, the same command we did earlier, previously we only had 2 routes for our directly connected networks. We had the 10 network 1012 and the 101, but the new one is this new S. And if we look at S in the decoder up here, S refers to a static route, and we've just trained this router how to reach 192.168.0 network, and we're saying that the next hop is 10.12.0.2. Let's talk about that. A hop. Think of a bunny rabbit jumping. So we have a bunny going boing, boing. Those are considered hops. So every router in the path is considered a hop. So if we said, well, from R1's perspective right here, how many hops does it take to reach the 192.168 network? And the answer would be, well, there's 1 hop and there's 2 hops. And if you ask that same question from the perspective of the PC, how many hops does it take to get? This PC might say, oh, it's 3 hops because I've got to go to my first router, and then it goes to the second router, and then it goes to the third router to get to its final destination. Now, fortunately, PCs don't have to worry about large routing tables, because a PC, we can just do this. Dear Mr. PC, you live on the network 10.1.0, and if you need to reach anybody who's not on that same network, you go ahead and forward it to your default gateway, and we tell the PC that this router is its default gateway. It's sort of like the Star Wars Obi-Wan Kenobi route. Help me, Obi-Wan, you're our only hope. So the PC doesn't have to learn the entire network. The PC just has to know the network it's connected to and the default router, also called a default gateway, to use in the event it needs to forward or get a packet to a non-local network. Okay, so is our work done? No, our work's not done, because even if we forward a packet, if R1 forwards a packet to R2 that needs to go to this network, what's R2 going to do? Well, let's go ask him. We've got some commands right here. We've got an interface. Let's go ask R2. Here's how you'd ask R2 what he would do with a packet destined for that top right network. We do a show IP route. And this is the syntax on a Cisco router. And look at this. Wow, he's got more routes. He's got 1, 2, 3, 4, 5. Really? So 1, 2, 3, 4. Where's his 5th route? Let's take a look. Oh, he has a directly connected internal address as well. All right. I just wanted to make sure we weren't getting something for nothing. So R2 also has something called a loop back interface. And there's testing purposes for, I shouldn't say testing as in certification testing. We can use loopbacks for various network functions. It's like a pretend interface that has an IP address. But the other 4 that I circled here are these bottom 4 that are also showing as directly connected. But you'll notice, out of this routing table, if R2 got a packet for 192.168.0 network, if it would look at its routing table and say, I don't know how to reach that network. I don't have it in my routing table. I don't know who the next hop would be, and it would drop the packet. So what we could do again here on this router is we could add a static route. Okay, this is painful already, because if you have a fairly large network and you're adding static routes for all of your networks, you're going to have to do a lot of manual configuration, and it's a pain, because if something changes, you've got to go back and add new manual routes. So instead of using static routes, which those were all examples of, we could change the rules and simply use dynamic routing for learning. Dynamic routing simply allows the routers to share information. So for this network, R3 would share that information with R2 saying, hey, if you ever need to reach this network, send it to me. And R2 could take that same information and say, well, Mr. R1, if you ever need to reach network 192.168.0, please send it to me. See, they're all basically telling the next person in line who to forward the packet to. And that type of routing, that type of dynamic routing, is called a distance vector routing protocol. Distance vector is when it's like telephone, the game telephone, where you tell somebody and they tell somebody else and they tell somebody else. So with the game of telephone, R3 regarding this network tells R2, R2 tells R1, and that's eventually how everybody learns how to reach the network 192.168. And one example of a distance vector routing protocol is something called Rest in Peace. Now, it's not that is the acronym for Rest in Peace, but RIP in the world of computer networks stands for Routing Information Protocol. It's simply a routing protocol that it's distance vector, and if you enable it for all of your networks and all of your routers, they will all share all the information, and you can have complete reachability without configuring a single static route. It won't take long to configure that, so what I'd like to do is do exactly that. I'm going to go back to R1, where I configured a static route. I'm going to take that out. I'm just going to take out that static route, because that way we show everything working without any static routes. So that's how you say take that away. In Cisco, speak is you put a no in front of it. And we just show IP route. We're back to our two directly connected networks on R1. Okay, so for RIP, I'm going to use a really cool tool. This is part of Secure CRT. It's not the end of the world, but it saves a ton of time in a lot of my configs. I'm going to click on View, and I'm going to say Chat Window, and I'm going to tell this that I want to send my chat to all tabs, meaning whatever I type in here, whenever I type in this chat window, is going to go to all four routers at the same time. Now, in this case also, just for the moment, the ISP, I've shut down these interfaces, so they're not being used at the moment. So it's just R1, R2, and 3 as the primary focus for our discussion. So if I wanted to enable the RIP routing protocol on all these devices, I would say configure terminal, which puts me into something called global configuration mode on a Cisco router. And again, the syntax, don't care too much about that at this point. The concept is what I want you to focus on. And we're going to go into a little separate room on each of these routers, and it's going to be called router RIP. So you notice how my prompt changed to config-router? That says visually, oh, you're inside of a little sub-compartment inside the router logically where you can configure RIP, routing information protocol related commands. And just for grins, let me go to each of these other devices, and you see on R2 and R3, it's all the same commands because all those commands are going to all the devices. And from here, I'm gonna say I want to use version 2 of RIP, and I want to take off something called auto summary. Auto summarization is where RIP likes to only advertise classful networks like class A or B or C with 8 or 16 or 24 bits. And this basically, with no auto summary, it says forget about that, just do what Keith wants you to do. And then I'm going to tell the routers that I want to include all networks. And this is a shortcut because it's not a Cisco class. I'm going to just tell you that command right there simply tells each of the routers to include all of its interfaces in RIP, meaning every directly connected interface is going to be sending and receiving advertisements with all the routing information. So here's what's happening in the background. And it takes a few seconds for RIP to converge because it's neighbor telling neighbor. But here's what's happening in the background. R1 is directly connected to the 10.1 network, so he tells R2 about that one. R2 learns about the 10.1 network, and R2 tells R3 about the 10.1 network. And R2 is also going to be advertising it this way, even though our service provider's interfaces are down, and he doesn't care about our internal networks anyway. At the same time, R3 is advertising the 192.168 network to R2, who's also advertising that 192.168 network to R1. And eventually, in a few moments, every router will have advertised all of its routes, and every router will now have full reachability with just a few basic, actually it's just these 4 basic commands for RIP. So let's take a look. Let's go back into our router config, and I'm on R1. And let's do a show, the same command we did before, show IP route. And there's our routing table. Now, this is showing us one page of our routing table. This is the R's represent RIP learned routes. If we scroll up a little bit, the R is right here. So that's how we learned about these networks. And if we went through each of these, we could basically identify all of them. So let's pick the 192.168 network. That's a fun one. So from R1's perspective, here's this network, 192.168. And if we find it in the table down here, which I didn't scroll down far enough for, so I'll do that now. There we go at the bottom. So let's take a look. So here's the 192.168.00 network. And now it's in the routing table. So if R1 got a packet from this happy user and it was destined to the 192.168.00/24 network, this router would know what to do. And it says this, I'm going to forward that packet, says R1 if I got it. I'm going to forward it to my next hop, which is 10.12.0.2. That happens to be R2's address. R1 knows how to get to R2, no problem. And I'm going to use my fast Ethernet 1/1 interface to go ahead and forward it to R2. Why? Why did all that happen? Well, it's because R3 told R2, and R2 advertised that network to R1, and because R1 learned it on the FA1/1 interface, and because R2 is the person who told R1 about it, that's why these elements show up here. It also shows that we had an update on that about 2 seconds ago. Now with RIP, Routing Information Protocol, it sends updates every 30 seconds. And it sends almost the complete routing table. There are some exceptions to that, but RIP says, you know what, things could change. I'm just going to keep advertising every 30 seconds, and hopefully everything will be advertised to everybody and life will be good. So that's RIP in a nutshell. And we could pick any one of these networks, like this one right here, the 172.16.1 network, and we could say, from R1's point of view, how would he get there? Well, R1's going to send it to 10.12.0.2, and he's going to use FA011. He's still going to send it to this guy. One other thing we should talk about for a moment, too, is this number right here. Because virtually every vendor has similar things. They don't all call it the same. But let's talk about this specific route again. And let's talk about this number right here. You know what that number is? That number is called a hop count. In RIP, the way RIP decides what the best path is, for example, maybe we have 2 or 3 different routers advertising to R1. In this case, we only have 1, but if we had 2 or 3 different routers, and they're all saying, yeah, I can get to that network, I can get to that network, with RIP, we would look at the hop count, right over here, and RIP would choose the lowest hop count as the best route and use that best route to go ahead and forward towards that destination. So if you look at the 2, what does that mean? It means 2 hops. So when R3 advertised R2 and R2 advertised to R1, the hop count that was advertised was 2. That's because R3 advertised it with a hop count of 1, meaning that network said R3 is 1 away. It's directly connected to me, but it'd be 1 away from you. And R2 advertised the hop count of 2. And that's why R1's routing table has a hop count of 2. If you take this network, for example, let's clear this off for a moment. If we take the 10.2 network right here, and that is being advertised to R1, look at that one. So it's right here. Here's the 10.2 network. Look at that. It's just 1 hop away. See that one right there? 1 hop away, because R2, when he advertised, said, hey, it's 1 hop away from you because I'm directly connected to it. That's the logic behind it. So that's RIP in a nutshell, and that's how it works. RIP, as a review, is a distance vector routing protocol. It's a fancy word. There's a lot of math that goes into it, but really you can think of distance vector as, okay, how far away is it, and which direction would I use to reach that network? So R1 could use, the next hop of R2, out interface FA11, and based on the number of hop counts, it's going to choose its best possible path. Now, that's not how every routing protocol operates, and it's important also to be aware that if we are working with routing protocols to learn, we want to make sure our networks can do something called convergence very quickly. Now, convergence, let's just write that out, convergence. What is convergence? Convergence is when everybody agrees. What do you mean, Keith, everybody agrees? Well, let's say that this network exists, and then let's say that we take it away and we shut down the interface. Now the network doesn't exist. I mean, that's how simple it is with routers. If we turn off an interface on a router and that router was the only connection to that street no longer is reachable. How long does it take for the world to find out about that network no longer being available? So let's demonstrate that with RIP. On R3, he's directly connected to that network. I'm going to power off R3. And before I do that, here's R1. We do a show IP route just again to make sure that it believes it has reachability through RIP to that network. In the background, I'm just going to pull the plug on R3. It's not going to be pleasant, but he'll be okay. So I'm just going to physically stop it. He's dead. So that little indicator right there indicates that I pulled the plug on him. And if we go back to R1 and we do a show IP route again, look at that. We still have that network in our routing table. And if we now the updates are coming every 30 seconds from R2. So it might take, and we're getting really close, so if we do it again. Look at that. Bless his heart. R2 is still advertising the 192.168.0 network. Now there will be a time, and it's like in 3 minutes, where R2, after no longer receiving any updates about that network, is going to say, "Oh, you know what? I better stop advertising that network because I haven't heard about them." And that will also eventually leak over to R1, who will stop hearing updates. But it's a nightmare. RIP converges really, really slow, and that's one of the many reasons we don't use it a lot anymore in production networks. It's just too slow to converge. It's not accurate enough. I mean, if this network really goes away, we want it to be gone. So let me bring up R3 in the background again. We'll reload him up. So he's starting in the background, so R3 should be happy here in a few moments. We'll give him a second to boot up. And that'll give us an opportunity to talk about the next type of routing protocol, and that is something called link state. Now, just like RIP is a distance vector routing protocol, put DV for there, OSPF stands for Open Shortest Path First. It's an example of a link state routing protocol. Now, this is pretty amazing because what happens with link state is we're not taking the word of our neighbor for everything. For example, regarding this network that was advertised by R3 to R2 and R2 told R1. So R1 is really, learning by rumor, the rumors that R2 is telling them about remote networks. Instead of doing that, with link state, we can simply do this. We can have R1 say, I know about the 10.10 and I know about the 10.20, and he can advertise that as something called a link state advertisement. And that advertisement gets listened to by R2 and then propagated to the other devices running OSPF. So at the end of the day, R3 is actually seeing the LSAs that R1 generated, and then R3 can say, okay, so I know R1 is directly connected to these two networks. I know R2 is directly connected to those 3 or 4 networks. And then R3 can use his own calculations called an SPF, shortest path first calculation, to determine the best way to get to each destination device. And that's what OSPF does. OSPF is an example of a link state routing protocol. And because it also is very easy to configure, let's go ahead and do it. So R3 is back, and I'm going to use some sweeping changes here again. I'm going to go ahead and do configure from the terminal, no router RIP. That will remove RIP from all these boxes. And let's do a router OSPF1. Again, the syntax isn't too critical, but the actual concept of understanding the difference between how link state routing protocol works and a RIP routing distance vector, that is critical. And I'm going to say network this is a fancy way of saying that I want all interfaces on each router to participate in a single OSPF area, and it happens to be called Area 1. And that's it. So having done that, let's take a look at the results. In the background with link state routing protocols, each of these routers are going to form a neighborship, a formal neighborship with each other. And they have to agree to certain things. For example, the MTU, that's a fancy way of saying the maximum transmission unit. On Ethernet, the general maximum MTU is 1,500 bytes. So one of the things that these two would agree to before they neighbored up and became really friendly with OSPF and agree to, propagate the advertisements from each other, they would have to agree on something like the maximum transmission unit. They'd also have to agree on what the network was between them. And there's some other properties as well. But they neighbor up, and then once they neighbor up, they keep track of their neighbors. And if I lose a neighbor, I can notify the rest of the world that that neighbor's gone, or actually, because the LSAs are no longer being sent, the rest of the network will converge much, much quicker. And there's a whole world that I look forward to joining you in another class on another day, maybe CCNA with Jeremy or some other class. But for now, link state routing protocols like OSPF converge very, very quickly because we're not taking secondhand information. We're getting information from the source. So let's take a look at what our routing tables might look like. You'll notice that, R3 has some adjacencies, and let's take a look at R1. Let me end this. So here on R1, if we do a show IP route, same command we did before, Now we have these routes that say, oh, I learned these via OSPF, and that's what the O stands for. And the OSPF is going to basically say how we learned it, and then it's going to go ahead and also give us a cost. Now this number here with OSPF is not a hop count. It uses a different metric. And a metric is a fancy way of saying how good or how bad a route is. So with RIP, we used hop counts. With OSPF, it's a cost. So the further away a network is, effectively, the higher number the cost is going to be. So it's just like golf, the lower is better. So with OSPF, these aren't hop counts. That is a cost count with OSPF. It still shows from R1's perspective. If we go down a little bit here, it still shows for this network. It has a cost of 4, which is internal to OSPF. So if it had multiple routes being advertised by multiple neighbors, it would choose one with the lowest cost. And it shows that the next hop is still 10.12.0.2. And it shows that the last update was that long ago. Wow. See, RIP updated every 30 seconds. Like, here's everything, here's everything, here's everything. OSPF, we establish neighbor relationships. And if nothing changes, we don't need to flood all the information for all of the network every 30 seconds. We can do it maybe every 30 minutes just to make sure it's out there. But with link state routing protocols, we advertise the links that we have, we maintain neighborships, and it converges a lot quicker. So for example, now, if we turned off R3, which I'm going to do right now. So on R3, if I simply said stop, so R3 in the background just died, so he's dead. If I go back to R1 and I say, dear Mr. R1, tell me about your routing table again, the show IP route, look at that, it's still there. It's still there, but it will converge quicker. It's going to take a few seconds for R3 to stop his neighborship with R2, meaning not reply anymore, that he's there. And after that timeout occurs, that route should go away. And let's take a look at what the timeout is. That's embarrassing. It should converge very, very quickly. Let's take a look. Show IP OSPF interface serial 4/0. I just want to look at the timers. Okay, so the dead timer is 40 seconds. And all that means on this interface to R2 is that if R2 doesn't hear from his neighbor within 40 seconds, he's going to consider that neighbor dead. And at that time, it'll go ahead and propagate that information and then R1. So as opposed to like 3 minutes, we have with a dead router a much quicker convergence time. And there's tweaks and tunes that we can do to make it even faster. Let's go back to R1. That should be at least 40 seconds. Show IP route, and sure enough. So that route is gone. And R1 no longer believes the 192.168.0 is reachable. So what have we learned? We've covered so far about the topic of routing. We've learned that routing is 2 things. We have the learning of routes, which can be directly connected or dynamically learned or statically configured. And then we have forwarding packets based on that information. Static and dynamic we've discussed. RIP is distance vector. OSPF is link state. And we also talked about the next hop. The next hop is the next person that this router is going to forward a packet to in order to get that packet to its final destination. And then we also discussed metrics. With RIP, the metrics was a hop count. With OSPF, it was a cost. And now I'd like to talk about something totally different, and that is a hybrid routing protocol. Now, a hybrid routing protocol is something that maybe uses neighborships to keep track of neighbors, like link state, but it also works like a distance vector routing protocol. In fact, there's only one on the street. It's called EIGRP. It's Cisco's. It's enhanced. It's proprietary. It's Enhanced Interior Gateway Routing Protocol. Enhanced Interior Gateway Routing Protocol. And it's not used that much anymore. It's a fantastic protocol, no doubt, but it's not used much because it's not open. Meaning, if you have Hewlett-Packard or Juniper devices, because EIGRP is proprietary, it would mean you all have to have all your gear from Cisco. But one thing about EIGRP that's really cool is that its metric is based on the bandwidth and the delay. It takes those two major considerations in when it calculates its metric to a final destination. So I'd like to demo that real quick for you as well, so you can see it, experience it. And to do that, I'm going to bring up R3 again. So in the background, we're starting up R3. Hopefully he'll be up in a moment when we get to him. In fact, before I start configuring, he needs to be up and active. But here's how EIGRP operates. EIGRP establishes neighborships, keeps track of its neighbors, it cares. And then when it has those neighborships, it advertises all the routes. And then it doesn't bother reflooding all of those routes every 30 seconds like RIP does, because it says, hey, if there's a change, my buddy will let me know. And so because of the neighborships and because of not flooding all the routes every 30 seconds, EIGRP is a hybrid, but what it really is, it's an advanced, enhanced distance vector routing protocol, because at the end of the day, it really is using the distance vector approach to calculating the path that it's going to use. And the metric is derived from bandwidth and delay. So that gives me a moment to get R3 up. And he is up and happy, or will be here in a moment. There he is. Okay, so let's go ahead and configure all these for EIGRP. I'm going to remove the OSPF1 router configuration, and then I'm going to add EIGRP. I'm going to say autonomous system number 1, so they're all in the same autonomous system, and I'll say network. I'll say no auto summary. Just like RIP, it does like to summarize to classful boundaries, and then we'll say network. This is another shortcut, just like RIP, that says everybody's in. Now, it's all converged. It's done. This router right now knows about how to reach everything. I mean, it's so darn fast. Show IP route. It's just everything is there. So the 192.168.1 network, the 192.168.0 network, this guy, R1 knows about it. The next hop is 10.12.0.2. I'm going to use FA11 as my exit interface to reach it. And here's the metric. So that metric is a function of bandwidth and delay calculation. So we're grateful for the mathematicians that have figured all that out for us. But the reason for a metric is if my router received 2 routes from 2 different sources, it would go ahead and use the lowest of the 2 metrics from that same routing protocol it learned it from to choose its best possible path. And if we take away R3, check this out. So up on R3, I'm going to kill it again. Sorry, Mr. And let's see if we can ping it. So R3's interface address is 192.168.0.3. So that verifies that we have reachability all the way to R3. It also verifies that R3 can respond all the way back to us. So he's got the routes back to us as well. So I'm going to kill R3. Sorry, Mr. R3, you're going down again. So I've turned him off. We'll just verify that he is dead, gone. And go back to R1, and we'll do a show IP route. Now there's still a hello factor involved that has to time out for R3 and R2. But you'll notice it didn't even take 40 seconds for that neighborship to time out. It is gone right now. So the 192.168.0 network is no longer reachable. And EIGRP, the big negative is it's proprietary. The great thing about it is it can reconverge very, very, very quickly. So let's do a spot check to make sure we've got all the pieces. Routing is 2 pieces, that is learning the routes and then making forwarding decisions. So as a router receives packets, it looks at the destination IP address. If that IP address is not itself, meaning it shouldn't decapsulate it any further, it then forwards it based on the next hop to the next router, and then that next router would make that forwarding decision to its next hop till the final packet reached the final destination. So we have static routes, dynamic routes, RIP, distance vector, OSPF, link state. EIGRP is hybrid, which is a really advanced distance vector routing protocol. We've already addressed the next hop, meaning the next router you're going to forward a packet to, and the metrics. For RIP, it was a metric of hop count. For RIP, it was the cost for OSPF, and our EIGRP, it also used, we'll just call it a metric, because it uses a custom metric based on bandwidth and delay and so forth. But with any of these, lower is better. So if you get two routes from the same routing protocol, the one that has the lowest metric is going to be the one this router is going to use for the path or for its forwarding decisions. So the routing table is what it refers to. The router refers to when it gets a packet that's not for itself, not for its own IP address, and it looks at the routing table, looks at the next hop, looks at the egress interface, the exit interface, and then forwards it along based on the routing table. Latency, let's talk about that for a moment. What is latency? Latency means slowness. So if you have a routing protocol that converges slowly, you could say it has a large amount of latency. That's one concept with routing. So latency meaning time, and for converging, time, large amounts of time is a bad thing. Also, if this happy user here is sending a packet to a server over here on this network, if the packet takes a long time to get there, that would also be a bad thing. So latency for regarding either convergence, meaning the network, everybody knows what all the networks are and how to reach them correctly, as well as latency for the packet being forwarded, are both negative things. So low latency is great, high latency is not great. And then finally, how does the world operate? Well, the world is a big place, and let's talk about IGPs and EGPs, and let's talk about those terms. IGP stands for Interior Gateway Protocol. And you and I both know that a protocol is another code name for rules, right? From our earlier discussions together. So if we have an interior gateway protocol, what is that? That's a routing protocol. A routing protocol is a method that we can use where the routers train each other on how to reach networks. So 3 examples of IGPs, interior gateway protocols, are RIP, a distance vector IGP, OSPF, a link state routing protocol, or IGP, and EIGRP, which is a proprietary / hybrid / advanced distance vector IGP. That's all that is. So IGP is a fancy word for saying an interior gateway routing protocol or a routing protocol you're going to use inside your own company. And that's exactly what we did here. This is all inside of our company. But what about the internet? The internet's a bigger place. So let's say you have a service provider, and let's call him service provider A, and we are using that service provider. But in another part of the world, we're using service provider B, and in another part of the world, we're using service provider C. How does that all work? Because all the internet routes, they all have to be shared. And the way we share routes between these different service providers is something called EGP, External Gateway Protocol. And when you see EGP, I want you to be aware there's only one of them. Now, it's the 21st century, and things could change in the future. But at the moment, the only exterior gateway protocol is BGP. So if you kind of do this, it kind of looks like it. So BGP stands for Border Gateway Protocol. It's kind of like Sam's Club. In the part of the world I live in, there's a place called Sam's Club where you can buy like toilet paper by the crate, and you can buy, food by the bushel. It's just huge quantities. When these service providers, they have like, maybe this guy's got 20,000 routes, and this guy has 40,000 routes, and this guy has maybe 70,000 routes. They need to share those routes with each other to make the internet go. In fact, on the internet, there's more than 400,000 routes. So how do we share those routes? Well, we use a routing protocol for training, for learning. And a routing protocol between service providers, the routing protocol is called BGP, Border Gateway Protocol. So that's all it is. Border Gateway Protocol is a routing protocol that can be used between domains. Domains is a fancy way of saying between groups of management. So service provider A is Sprint, and service provider B is AT&T, and service provider C is some upcoming star. And there's lots of them. And so we'd use BGP cooperatively to share routing information between the service providers so that everyone would have not everyone, but all the service providers would know how to reach all those 400,000 plus routes and networks that exist on the internet today. And the number is growing. With IPv6, we have a whole nother set of routes and a whole nother set of routing tables. And fortunately, BGP supports IPv4 and IPv6, so it can support either one of them. So the ins and outs of switching at layer 2, I put that in there just so we could remember exactly where switching happens. And it's a layer 2 function because we're making forwarding based on layer 2 addresses. So here's our topology that we've been working with so far throughout this class. And we focused on the routers in the previous little piece here in this nugget. And I'd like to focus on this icon and this device, which is better known as a layer 2 switch. So I've removed away the larger topology for a moment so we can focus on the switches. And let's say that you and I walk up to a switch. Let's say we go up to switch 1 right here. And we say, "Dear Mr. Switch, what is it you do for a living?" The switch would say, if it could speak English, it would say, "Well, here's what I do. What I do is I memorize or I learn MAC addresses. And I learn what ports they're associated with." So just like routers learn network addresses and where they are, either through static configuration or dynamic routing protocols are being directly connected, a switch is going to learn MAC addresses. And here's how it does it. It's going to eavesdrop on every single frame that comes into it. So let's say that PC2 has a MAC address that ends with 22. Now I know a MAC address, as we learned earlier, is 12 characters long, and these are only 2, but it makes it easier to write it out. So we'll say that's the MAC address of PC2, and this is the MAC address of PC33, and this guy is on port 1, and this guy's on port 2. So when PC2 sends a frame into the network, which only takes a few moments, your computers, when they boot up, they're doing stuff on the network almost as soon as they can speak. So there's going to be frames going into the network. As soon as this PC sends a frame in, that frame at layer 2 of the OSI reference model, that frame has a source MAC address and a destination MAC in the actual field. In fact, let's take a moment and let's look at a MAC address through a protocol analyzer that we looked at earlier. So here's a capture that we can use as a reference point. And we're interested primarily in the layer 2 header. So here in the layer 2 header, we've got a destination MAC address. And we also have a source MAC address. So here's what happens. I'll get a different color. The switch pays special attention to the source MAC address. So over here, as the frame came into the switch on port number 1, if the source MAC address ended in that 22, for example, the switch would build a table. It would say, okay, I just learned something. I've just learned that on port 1, there actually lives a MAC address of 22. So that's the port, and that's the MAC address. And again, we're using the 2 characters just to make it a little bit shorter. And as soon as PC3 sends a frame into the network, the switch would say, oh, on port 2, there's MAC address 33. Now, how does that help anything? Why is that beneficial? Well, the reality is a switch doesn't like to forward everything every time. Unlike a hub, a switch does what's called selective forwarding. So it means this: if PC2 was sending a frame at layer 2 of the OSI reference model, and it was sending it to the MAC address of PC3, the switch would take that. I'll get a different color here. It would take that frame and say, oh, I know exactly where that destination MAC address lives. It would send it here, and it wouldn't bother sending it to any other port. So if we had other devices on these ports here, like PCs or printers or what have you, they wouldn't even be bothered by receiving the bits because the switch only makes forwarding decisions based on the layer 2 addresses. That's it. That's the primary job of a switch, is to learn where MAC addresses live, off of which ports, and then go ahead and make forwarding decisions based on that. Now, what happens if there's a frame that comes in the network and it's destined to, let's say it's destined to this address right here. And let's say for whatever reason, the switch has not memorized where that MAC address lives yet. This one right here. What does it do? Well, it's going to make an error on the side of caution, and it's going to say, well, I don't know where that MAC address lives, so I'm just going to flood it to every other port except for the, where it came in on. So if it was PC2 sending the frame, it would forward it out to PC3 and all these other devices would get it because the switch doesn't know. So it's going to forward the frame to everybody who's going to receive it, and then it's up to the end devices to decide whether it's relevant for them or not. So that, my friends, is the concept of layer 2 switching. So we've taken a look at what is layer 2 switching as far as memorizing layer 2 addresses and making forwarding decisions only to the ports that need it. And how is it done? We just talked about that as well. We memorize MAC addresses based on frames that we see coming in. And once we know MAC addresses, we make forwarding decisions only to the ports that need them. Now, let's take a look next at collision and broadcast domains. And I want to draw, just for a moment, the old hubs. Now, the old hubs from Ethernet hubs from many years ago, we used them back in the 90s, and we don't use a lot of them today at all. But a hub is not intelligent. It's a layer 1 device. So if we have a PC here, let's see, PCA, PCB, PC and PCD. And if we have a hub, when we have a frame of data that's sent in, that frame of data, because a hub is a layer 1 device, all it knows is bits. It doesn't know anything about organizing those bits into layer 2 frames or anything else. The hub will simply send those bits out every other port. Every other port except the one that it came in on, for example, right here. So that's what a hub does for a living. So let's talk about collisions for a moment. What is a collision? Well, let's say that PCA and PCB both want to send traffic onto the network in this hub network here. I call it a hub network. That's kind of funny. But they both want to send data into the network. What do? They use something called carrier sensing multiple access with collision detection. Now, that's a whole bunch of letters there. Let's talk about them. Carrier sensing simply means, hey, Mr. PCA and PCB, if you want to talk on the network, you put your ear out there and you listen electronically. You listen and see if there's already a carrier present and if it's being used by somebody else. See if in a shared hub environment, only one device can talk at a time because the bits are being sent everywhere else. So with carrier sensing, it means please listen to see if the road is clear before you cross the street, before you put your data on the wire. Multiple access means, guess what? There's more than one device on that network, or could be, that may want to use it. That's all that means. So listen to the wire before you send to make sure that wire isn't being used by somebody else sending their data, and there could be multiple devices. Well, what happens if two devices send traffic at the same time? So PCA both listen, and PCB both listen. They both send their bits into the network at the exact same time. There's going to be a explosion. Now, it's not really an explosion, but what they do call it is a collision. So a collision can happen in a hub environment where you're sharing all the bandwidth. So when there's a collision, here's what happens. Both devices, as they're sending, they're also paying attention to what they're sending, and they see signals on the wire that are not their own. And so when these two signals are mashing with each other and interfering with each other, both devices back off, PCA and PCB. They would say, oh, stop. They also send a little notification like, I'm sorry. They call it a jam signal. They both send a jam signal into the network to let everybody know there's a little problem. They back off, and then they can try again for their retransmission. And it's no big deal. It happens all the time in a hub environment, but it does slow the network down because only one device can communicate at a time, and that's why a hub has one collision domain period. So if we had a hub here connected to another hub here, connected to another hub here, and we had PCs. Basically, out of all of that, the whole giant thing would be one giant collision domain, meaning they're all sharing the bandwidth because the bits, as the bits from this guy go into the network, they would go up here and out here and up here and out here, and it's one giant opportunity for a collision, and that's why one collision domain means. Also, it's one giant broadcast domain. What does that mean? Well, a broadcast as we have touched on in earlier nuggets, is when a machine needs to send a message to every other device. So let's say that this PC up here wants to send out a broadcast message. So at layer 3 of the OSI reference model IP, it might look like on the 10.1.4. network, it might look like 255. That'd be a layer 3 broadcast. But that gets converted at layer 2 to a layer 2 broadcast, which would be FF, 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 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 characters of Fs, which represents 48 ones. So basically all those the destination layer 2 address would be put into the network. Now the hubs, they have no clue about layer 2 anything. So the hub is simply repeating all the bits, and then every device on the network is going to look at those and say, oh, it's a broadcast, and they'll continue de-encapsulating to see if there's anything interesting at layer 3 or possibly higher than layer 2 for that device. So in a hub environment, we have one collision domain and one broadcast domain. It means everybody could collide with each other, and a broadcast is going to be seen by everything. So how does that compare and contrast to a switch? Great question. Well, in a switched environment, the rules are very much different. So if we have a switch, and let's go ahead and take a switch like this. Now there's a switch. And we have PCA, PCB, PCC, and PCD. All right, and we got those 4 devices, but now it's a switch. Let's talk about the collision domains again. There's no collisions with a switch. It's like, well, Keith, how does that work? How do you pull it off? See, a switch doesn't first of all, a switch doesn't forward all the frames to all the ports. It's intelligent about it. It also has a little bit of buffer. So it has buffer is a fancy way of saying it can store stuff for a short period of time. So if PCA is talking to PCB, he forwards his bits into the switch. The switch forwards them out to PCB. Doesn't bother PCD or PCC, these two guys. But also, we're using different sets of wires. See, in our unshielded twisted pair cabling, we have 2 pairs of wires. And with a switch, we use one of those for sending data and one for receiving. And when we do this, we use 1 pair for sending, 1 pair for receiving, and we're using a switch, we get something called full duplex. And full duplex means that we can send and receive at the same time. So PCA and PCB could be having a conversation. PCD and the PCC right here could be having a conversation. And the switch is going to keep all that separate. Now, if there's a situation where multiple devices are sending to one device at the same time, the switch can sort all of that out on the back plane of the switch in the background, kind of hides it, so that there's never a collision. So what does this mean if there's no collision? That means that PCA has its own collision domain and PCD has its own collision domain. So these circles right here each represent collision domains. And having multiple collision domains is a good thing. In fact, on a 48-port switch, guess how many unique collision domains we have? We have 48. Every port on a switch is its own collision domain. That means it's like having your own dedicated freeway. You'll never see another car because the switch is sorting all the traffic out in the background, and you have dedicated freeways to every single PC. So do switches cost a little more than a hub? Yes. Today, a low-end switch and a low-end hub are both going to be fairly inexpensive. And in production environments, we don't actually use hubs anymore. It's all switches, partly because of this. Now, one last scenario that I want to run you through, and that is, what about broadcast domains? Well, if we have, let me clear the screen here. If we have 3 switches tied together, and we have PCA and PCB and PCC, Need to come up with another naming scheme. That bothers me. So we have 3 devices hanging out there. If one device sends a broadcast frame into the network where the layer 2 address is FFFF, 12 characters of F, which means all ones in binary, the switch does not know where that MAC address lives. And so what it's going to do, what the switch is going to do, it's going to forward it to all other ports, including the one that's connected to switch 2. And switch 2 is going to forward it here and to all other ports, including the port connected to switch 3. And switch 3 is going to forward it out. So whether you have a hub or switches in their default state, they're both, if they're connected together, we're going to have one broadcast domain for switches and hubs alike. So in summary, with a hub, you have one giant ugly collision domain. With switches, every individual port is its own freeway. There's no opportunity for collisions at all. So you have individual collision domains for every single port on the switch. But for broadcasts, switches and hubs work very similar to each other. A broadcast is going to be sent everywhere where there's connectivity. So we take our analogy up here. I've got PC1, PC2, and PC3, and I've got some interconnections between the switches. So maybe our company's growing, we start daisy chaining the switches together like this. And if PC1 sends a broadcast into the network, that'll be sent out to here. The switch will also send it down this port and this port. And so once the switch receives it on this port in, it'll also forward to that. So all your devices with your interconnected switches is one giant broadcast domain. It's the range of where a broadcast would be seen. So we've covered how switching is done. We've taken a look at collision domains, which is where a collision between 2 devices can happen. It's a bad thing. So having more collision domains means no collisions or less collisions. And then spanning tree protocol is our next topic. So let me change this graphic out for another. Actually, let me preview this one. Let me premise this by saying, if a switch does what it's supposed to do and forwards traffic, there is a problem with the broadcast. And let's start there. And let's use this topology. So we send a broadcast frame here. That broadcast frame goes out here, and then it goes out here. And I'll leave this port off for a second. It goes here, but it also goes out here, and goes in here, and goes out there, and in there, and out there. You with me? No problem. We just want to make sure that every port, everybody has a chance to see this broadcast frame. But here's where it gets ugly because of this cable configuration. If the broadcast goes in here, we're ready for lap 2. And what do you mean, Keith, lap 2? Well, this broadcast that made it all the way around, what does the switch do with it? Well, the switch is going to feed it out. I'm going to put this new color as lap 2. It's going to forward it out, and it's going to go in here and out there and down here and here and here and here. Okay, and it's time for lap 3. No way. You're kidding me, right, Keith? No, I'm serious. This is bad news. So for lap 3, it goes out here, it goes out here, goes down this way. And what you're seeing visually right here, this is what we love to call a layer 2 loop, and it's ugly. And then we go to, round 4. And layer 2 loops, unfortunately, there's nothing to stop. Well, there's some things that could stop them. I guess we could turn off the equipment. But at layer 2, in the header, there's no mechanism that can say, hey, this frame has been around too many times. Let's kill it. There's just nothing there. At layer 2, you have the destination MAC address and the source. So there is a strong problem about having a physical configuration like this. So why would we even do it? The reason in a production environment we actually cable it redundantly like this is so that if this link breaks, we can still have connectivity. Or if this link breaks, we still have connectivity. Or if any single cable failure between the switches, we still have fault tolerance. But the problem is we have a loop. And that loop is a real problem, and that's why our commercial switches today have a feature that's running, and it's called the spanning tree protocol. Let me bring in a different diagram, and I'll walk you through the details of how spanning tree operates, and then we'll take a look at a live interface to verify some details of it. So with this topology, we can see the details of what we're going to do with spanning tree a little bit more clearly. The problem still remains in these 4 switches. We have them all connected together, and it's redundant. What do you mean, Keith, it's redundant? Well, if any single link fails, we still have connectivity because the other 3 are still in place. And of course, off to the sides, we'd have things like PCs that are also connected to these switches, and servers, and routers, and all the other network devices that we have our networks for. Those are still present. I just want to focus on these 4 switches for a moment. So we've already identified the problem of a loop. And the loop actually, unfortunately, doesn't just happen in one direction, like the loop going this way. If there's a broadcast, it's also going to go this direction as well. You've actually got 2 loops going, one clockwise, one counterclockwise, and it's an absolute nightmare. So spanning tree comes to the rescue. Now in Network Plus, our objective is to understand what spanning tree does. And the answer is spanning tree stops, it identifies and stops layer 2 loops. So let's talk about how spanning tree does this magic. In Alaska, they have this race called the Iditarod, and it has some sled dogs, and somebody was, one of the mushers, that's the guy driving the sled dog team, he had 2 lead dogs, and they were fighting. And he walked up as these 2 dogs were fighting, and he hit one. He hit one of them, and the dog just he got his attention, and the musher went back, and the dog started racing normally, and some onlooker said, wow, that's kind of mean to hit the dog, but what's your secret? What are you doing? And he said, you have to know which one to hit. And the secret of spanning tree is that spanning tree is going to identify a loop, and it's going to block at least one port where it sees the loops, so there won't be any loops. Literally, that's how it does it. Now, the mechanism for spanning tree to do this magic, it's going to identify something called a root bridge. Now, a bridge and a switch, same logical functionality. So in spanning tree, we're going to identify a root bridge. And with spanning tree, it's like golf. Golf, the person who has the lowest score wins. So each of these switches has something called a bridge ID. And that bridge ID is made up of 2 parts. There's a priority number, and there's also a base MAC address. So that means that if I have these 4 switches and the priority happens to be identical on all of them, then it would be the device that has the lowest base MAC address that would become the root bridge. But in any case, the bridge ID, the device that has the lowest bridge ID becomes the root. So let's say that switch 1 becomes the root bridge. Why? Because it has the lowest bridge ID. It advertises these BPDUs. Those are bridge protocol data units out. And he's not bragging. I mean, BPDUs are sent, and that's how switches know what the other guy's BPDU is. So the root port, the root switch, sends out all of its interfaces, the BPDUs, and the other switches say, okay, great. Switch 1, he won the election. He's the king of the hill. He's the root bridge. And so what we're going to do is we're going to see if there's 2 interfaces or more that are receiving these BPDUs. And here's the magic behind that. If switch 4 receives a BPDU here, and he also receives the root's BPDU here, switch 4 knows that, oh my goodness, I have 2 paths to get back to the root. There is a loop. So the magic is that BPDUs are sent out, and devices where they see BPDUs coming in on 2 different interfaces, if they're coming in from the root, so the root BPDU would be advertised this way and this way, and now switch 2 has a question, what do I do? Well, spanning tree is going to do this. Spanning tree is going to take one of these ports, and it's going to put in blocking state and allow the other port to do forwarding. And that's what spanning tree does for a living. And there's a whole week, literally, that we could spend on some really cool things on spanning tree. But for Network Plus, our goal is to understand what it does. Number 1, it stops layer 2 loops from happening. How does it do it? It identifies parallel paths from a layer 2 perspective, like we have right here, and it then blocks on at least one port. So I'd like to show you this in action because it would be a good thing to see as well. So let me bring some switches in, and they're all ready to go. They're so excited. They've been, prepping for the last 45 minutes in preparation for this. So let me shrink this a little bit, so we can see our topology. There we go. That's like perfect almost. All right, there's switch 1, switch 2, switch 3, and switch 4. Okay, so that's these 4 switches. And the commands, whether you're on Juniper equipment or Cisco or somebody else's, the commands might be slightly different, but the concepts are the same. So let's go to switch number 1, and let's do a show spanning tree. So show spanning tree has a lot of cool output. I'll scroll up a little bit here. And let's start off with this. So here the switch 1 is saying, oh, my priority is 28673, and my MAC address, my base MAC address is this number. So these two numbers right here make up what we affectionately call the bridge ID. These two guys right here. So if you said, what is the bridge ID of switch number 1, you'd say 28673, and then you'd put maybe a period just for fun, 001C, B148, 1E80. And that is the bridge ID for switch number 1. A lot of people often get a little bit confused because they think, oh, now these ports here, they're ports, so those interfaces have MAC addresses, right? But those MAC addresses are not used for this bridge ID. There's like an internal base MAC address that's being used for that purpose. So this MAC address right here is literally not being used on an interface anywhere. It's actually just internal to the switch. So his bridge ID is this one right here. And we look at the details of this. It's also saying that this bridge is the root. So basically the election has been done. It turned out that switch 1, just by chance or based on my configuration, won the root bridge election. So what he's going to do, because he won, the root bridge is going to forward on all of its ports. So here on switch 1, it's got gigabit interfaces, but a little confession to make. I have them running at 100 megabits per second. So they're capable of gigabit speeds, but everything's running at 100 megabits to make it nice and equal. So on a device, when it is the root bridge, it's King Kong, and all of its ports are going to be forwarding. There's no blocking whatsoever on the root device. So another way to identify that is to look right here. So we have these 3 ports are forwarding. So gig 1 isn't shown in this diagram, but it is forwarding, and gig 0/13 is forwarding, and 14 is forwarding. So a designated port, what it really means is that it's an interface that's forwarding traffic away from the root. So if you think of traffic moving away from the root, that would be a designated port. Because he is the root, all of his ports are going to be designated. So he's going to be designated forwarder on both ports. So let's go around. Let's go to switch 2 next, or switch 3 over here, and take a look at switch 3. If we look at switch 3, and we do a show spanning tree. In fact, I'm going to move this up just a little bit and close that, scooch this over. We don't need that much width, and then we can see more of the output. All right, thanks for playing. All right, so we'll do a show spanning tree. And what this is saying, he says, I know the root bridge is out there, and here's the information for the root. And he learned that from switch 1. He also knows that he's not the root, and check this out. The reason that this device is not the root is because his priority, his number, is higher. So the lower priority number of switch number 1 caused him to be root, and the bridge ID of switch 3 that we're looking at is higher. Just explaining why switch 3 didn't win. We weren't picking on him. He simply didn't win because he had a higher bridge ID. Now what switch 3 is saying is that I've got port 13 and 23, and one of them's a root port and one of them's a designated port. Let's take a look at 13 first. Port 13 is a root port. And every switch that didn't win, so here we have the root bridge. When you see root bridge, I want you to think King Kong. He's King Kong. He won everything. And every other switch has to kind of bow and honor that switch. And the port that switch 3 is choosing to forward traffic toward the root is called the root port. And you're only going to have one of them on a switch. So if a switch had hundreds of parallel connections, we're only going to have one root port on all the other switches, each of the other switches that are not the root bridge itself. So this is a root port forwarding towards the root, and the other port is a designated port. What does that mean? Well, the designated means we're forwarding away from the root. So this is a designated port that's forwarding. You could also say this is a root port that's forwarding because it's absolutely true. So what's next? Let's go take a look at switch 2. Somebody's got to block. Somebody has to block in this topology so there won't be a loop. So let's go over to switch number 2, and we'll do a show spanning tree there. So here's the show spanning tree for switch 2. Now switch 2 is interesting in the fact that port fast Ethernet 0/23 is blocking. See that block right there? That's basically saying that I'm blocking and I'm not forwarding, and FA 0/24 is a root port, and the root port is in the forwarding state. That means on switch 2, the port that it's using to forward traffic towards the root is FA 0/24, and we're blocking on port 23. Now you might ask, how does it decide? How does it decide where to block? And these spanning tree protocols, it's a good shopper. I want you to think of that. If you needed to go out and buy, let's say you wanted to go out and buy a router. You want to buy a router. And you could get the exact same router for $1,300, or you could get it for $1,700. And it's exactly the same, exact amount of service, everything else exactly the same. The stores are both the same distance from your house. Which one are you going to buy? You're going to buy the one for $1,300 because it's less expensive. Well, Spanning Tree does the same thing as well. We have some costs involved that are advertised over links, and we have costs on ports. And so basically switch 2, if it felt that this port 23 had a lower cost, it would have forwarded there. But if it thought that port 24 had a lower cost, it would forward there. Now, if you have a switch like this and the cost is, let's say the cost is 38 for grins, and the cost is 38 here, so the cost is equal, how does it choose? The way it chooses between switch 4 and switch 3, which one's going to be, which direction it's going to go, is based on the bridge ID again. So in this case, switch 4 must have a lower bridge ID than switch 3 because switch 2 is choosing to go that direction. So if we went and looked at those devices, which we can right now, if we looked at switch 3 and looked at the bridge ID, oh, this is it right here. So the bridge ID on switch 3 is this. It's 3279 and the MAC address is 000E, and I got to jot that down. So let's 000E 8300, and if we look at switch number 4, who hopefully is going to come up for us here. So if the priorities are the same, the tiebreaker effectively is the second half of the bridge ID, and that's the MAC address. So if we take a look at switch 4, which is 00E38, and we go to switch 3, which is 00Z83, you can see that switch 3 has a higher number. 83 is higher than 38 for those numbers right there, and that's why the choice was made. So that's a good primer into the world of Spanning Tree. So let's remind ourselves what it does. Spanning Tree is the purpose of the ability to identify loops in a layer 2 network and stop the loop. How do you stop the loop? You block on at least one port in the loop, and you no longer have a loop. So if this network actually went away, this connection failed, this would start forwarding again, and we'd have our fault tolerance. So you can have your fault tolerance and non-looping, and life is a good place. Convergence refers to how long does it take for a change, if it happens, to be identified, or for the whole network to heal itself. Just like in routing, convergence was dealing with how long does it take for the networks to all realize, the routing tables to all realize which way to forward traffic for routes. Well, in a switching world, we have the same concept. So if we change something, for example, right now, switch 2 believes that the best way to get up to switch 1 is through port 24. That was its root port. But what if switch 4 went bye-bye? So let's just verify that on switch 2 for a second. So the root port is port 24, right there. So if we rebooted switch 4, which I'm going to do right now, I'm going to save its config. I'm going to reload it. It'll take at least 3 to 4 minutes on this box. So switch 4 is gone. It's no longer there. So how long is it going to take for our switch 2 to realize that, oh, there's a problem and I need to start forwarding through port 23? There's 3 different flavors of spanning tree. There's the standard IEEE spanning tree, and it has a number, and that number is 802.1, D as in David. There's also a standard of spanning tree called rapid spanning tree, 802.1 W, for WAPID, like Bugs Bunny and Elmer Fudd, or WAPID spanning tree. And that's the numbers for it. So this is the group that was responsible for the standard, and that refers to the standard itself. So 802.1 W is rapid spanning tree. There's also another flavor called 802.1 S for multiple spanning tree, which we'll save for another day. So this converges slow. Convergence time is slow, fast. And what happened with 802.1s, that's also fast. They borrowed basically most of the features in rapid spanning tree and put them into multiple spanning tree. So if we want to go back to, in our case in point, if we go back to switch 2 and we say show spanning tree again, now it says sure, no problem. So I'm going to be forwarding on port FA0/23 because I don't even see, there's no options on FA024. I'm not getting BPDUs from switch 4. Nothing's happening there. So my only option is FA0/23. It's also preemptive. So if we waited long enough for switch 4 to come back up, spanning tree would converge again, and he would go back to forwarding here, and he would go back to blocking here. But at the moment, there's no loop, but if we waited another 5 or 6 minutes, it would indeed come back for that. So let's see if we've covered all of our objectives here. We've taken a look at convergence now, which is fantastic. And the next piece is VLANs. Oh, VLANs. Let's talk about VLANs for a moment. VLANs are fantastic. Let's say we have a switch right here, and it's a whopping 8-port switch. 1, 2, 3, 4, 5, 6, 7, 8. Now in our production switches, they have these big cages and chassis, and they have slots. And each of these slots can have like 48 ports each. So we can literally have hundreds and hundreds of switch ports available in one physical device. But here we'll just use 8. So let's say we have some PCs. And let's say PC2. And over here we have PC3 and PC4. Those PCs are all really happy because they're all able to communicate with each other and life is good. And then we get a new department. And this new department is going to be set up, let's call it engineering or sales or human resources or some department, and they get a couple computers. Well, when they're getting their computers, they're thinking, oh, we need to buy a new switch to support this new department. Well, if there's only going to be 2 or 3 people in the new department, what we could do is this. We could put those new users on these 2 ports right here. We'll call this PC5 and PC6. We can put them both on those ports, and I'm going to use, through the magic of color coding, we could create what's called a virtual local area network. That's what VLAN stands for. It's a virtual local area network. And if I tell the switch, hey, this is part of VLAN 3, this port is VLAN 3, this port's VLAN 3, and this port's VLAN 3. And then for our new department, I tell these two ports that they're in VLAN 4 and they're in VLAN 4. The devices, the computers, don't know anything except that PC 1, 2, 3, and 4 are all on the same broadcast domain, and PCs 5 and 6 are also on the same layer 2 broadcast domain. And without doing anything else, these two sets of users wouldn't be able to talk to each other because they're totally isolated from each other. So when you hear the concept of virtual local area network, that's all we're talking about. We're talking about logically separating some computers from others, and they call it a virtual local area network. So these customers right here might be on street number 10.1.0.0, and these customers in red might be on street 10.2.0.0, two different logical layer 3 street names, and they also have two different broadcast domains at layer 2. It's sort of like having a 2-port switch here and a 4-port switch. And then as new devices come on, you can decide, what do you want to do with this port? Do you want to make it a member of 3 or 4? Or do you want to make it a member of a completely different VLAN by assigning that port to a different number? And that's how VLANs operate. So one last piece. Let me clear off this. And let's talk about something that's real and important and also pretty darn cool. And that is, what if you have multiple devices? Let's go ahead and draw again. Let's say we have 3 switches. And we have switch 1, switch 2, and switch 3. And let's say those are in 3 different buildings. We have building 1 and building 2 and building 3, and they're all connected with a cable that connects with Ethernet, one switch to the other. If we wanted to have somebody, say we have some users here, let's call it sales. We have a sales PC, and we have a salesperson in each building. And these buildings are fairly close geographically, so it's still a local area network. So we have a salesperson in each building, and we have a human resources person in each building. I'll call it HR for short. So there we have just 2 users on each switch in each building. But we want them to be separate. So how do we do that? We want all the human resources to be in one VLAN. We want all the salespeople to be in this different VLAN. How do we do that? The same exact way we did previously. We would go to this port on the switch and we'd say, you're a member of VLAN 3. This port on this switch 2, you're a member of VLAN 3. This port on this switch, you're a member of VLAN 3. And that way they're isolated from the sales. And I'll put sales in VLAN, let's call them VLAN 6. So by controlling the ports on the switch, you control what VLAN they go into. So then we have the problem of, well, what happens if somebody in sales sends a broadcast? If somebody in sales sends a broadcast, what happens on this link right here? And let me show you the problem. So let's say the salesperson sends a layer 2 broadcast, and it goes into the switch. The switch, because it's a broadcast, says, oh, I need to forward this to every other port, but this time it says that it's in the same VLAN. So it looks at all the other ports in VLAN 6, sends it there, but if this port isn't in VLAN 6, it's not going down. So one option is we could assign this port to VLAN 6 and this port to VLAN 6, but then when the customers from VLAN 3 try to send broadcasts, they can't get down. So here's what the magic is of this link, this pink link, right in the middle. We're going to make it something called a trunk. And trunks are actually quite simple. A trunk says, I'm going to carry multiple VLANs, meaning I can carry broadcasts and required traffic for VLAN 6 and 3. So we could allow VLANs 6 and 3 on the trunk, and then it could go down. Well, Keith, that's fine by letting the broadcast to go down, but how does the receiving switch know when it gets a broadcast whether it was a broadcast for VLAN 6 or for VLAN 3? That is a very good question. And what we're going to use is we're going to use jackets. I want you to think of jackets. So here's a jacket, and take a look at the color. The jacket's red. Go red, go red, go red. And then we have another jacket or t-shirt, whatever you want to call it, and that's blue. And we might say this is VLAN 3, and the red one's VLAN 6. All right, so there's our jackets. So what we're going to do is, before switch 1 forwards a frame down the trunk from switch 1 to switch 2, it's going to take a moment and think to itself, oh, okay, this frame that I'm about to send from me to switch 2, it came from somebody. And what VLAN is it associated with? Did it come from a VLAN 6 user or a VLAN 3 user? Because I'm going to find out what VLAN it came from, and I'm going to apply the correct color to it. So if a salesperson generates a broadcast, before it gets sent over that trunk, we're going to go ahead and mark that frame with an extra little field that tells the receiving switch, oh, this is a broadcast for the red VLAN. And the technology for that is called 8.0. Well, the technology is called trunking, and the standard we use today most of the time is 802.1 Q, as in quiet. And all we're doing is we're adding an individual tag to a frame just on the trunk, so that the receiving switch can say, oh, this is for VLAN 6, or oh, this is for VLAN 3, and not have a mystery about what VLAN it's for. Let me show you the literal tag that's added when a frame is sent, and we'll use a protocol analyzer to do that right now. And here's a good one we can use. So we'll open this up, and we'll take a look at layer 2. So at layer 2, we have this frame of data that is sourced from this MAC address right here. And look at that. Somebody's manufactured that. That 10.10.10.10 is not something that you would get natively on a network adapter card as far as its network interface MAC address. But there's the source MAC address, there's the destination MAC address, that's all well and good. And with 802.1q, and that's what we're looking at right here, we're actually adding one additional piece of information, and that is we're adding the ID, the VLAN ID. So it's like the jacket. So when this, let's say it's coming from this switch going down to this switch, when he sent it, he added the 802.1q header, and in that header, the primary piece I'm focused on right now is the VLAN ID. So when this switch down here receives it, the switch says, oh, it's a broadcast, and by the way, it's for VLAN 2. Thank you. I will forward that to all my other ports that are associated with VLAN 2, including any trunk ports over here. And when switch 2 gets that, if it was forwarding out both interfaces, it would forward it also to and tag it along. But in our spanning tree analogy, we know that this one's blocked right here, so it would end. So the happy client here, who sends out a broadcast, if he happened to be connected on VLAN 2, the broadcast would be tagged VLAN 2 here, go to this switch, be tagged VLAN 2 here, sent to this switch. It would also go out this port, if it's also a trunk, tagged as VLAN 2, and it would be sent out here as well, tagged as VLAN 2, except because we're blocking, we're not receiving any data frames, any transit frames. So even though switch 3 would send it down, because he's a designated port for that segment, switch 2 wouldn't receive it and process it on this interface. So that's how tagging works with 802.1q. Let's just do a quick check, make sure we get all the pieces in this switching section. What is switching? It is the logical forwarding or forwarding of frames based on layer 2 addresses, and switches don't forward if they don't need to forward and they know where the MAC address is. How is it done? Switches memorize source MAC addresses, they associate those with ports, and then when they see frames going to any MAC address in their MAC address table, they forward directly, and they don't bother forwarding it to all other ports like a hub would. A collision domain, every port on a switch. That means if I have a 28 port switch, it's got 28 different separate collision domains, and that means those 28 clients connected to those collision domains won't have a collision. And a broadcast domain, a layer 2 broadcast domain, is the same on a switch and a hub. All the other ports on a hub are in the same broadcast domain, meaning they'll see a broadcast from another device. On a switch, all of the other ports in the same VLAN are in the same broadcast domain. There can be loops like we have right here. So if we do have a physical topology where we have parallel paths between any of the network elements, so for example between switch 1 and switch 2, there's two paths. How do we fix that? Spanning tree finds the root of the spanning tree by finding the device with the lowest bridge ID, and then it finds the furthest away point, the slowest connection point, and will block on that. And the convergence is simply the time it takes for the spanning tree to figure out all the devices to agree on where we're forwarding and where we're not forwarding. So people often ask, what happens if you turn off spanning tree? Well, if in a topology like this, if you turn off spanning tree, you'll have a loop. And the loop will be the most of the traffic on your network will be the broadcasts that are looping through, and user traffic will come to almost a standstill. VLANs is taking a switch and carving it up into multiple different layer 2 broadcast domains. So these two ports could be in VLAN 2, and these two ports could be in VLAN 6, for example, and the devices connected would only be able to communicate with other devices in their directly attached VLAN until we introduce some other way of moving that traffic, like a router, to move it between the two different networks. And 802.1q is a way of tagging. So if we want to set up trunks between our switches, the trunks will simply tag the frames. So every frame, every user data frame that's being sent over the trunk will be first tagged, specifying exactly what VLAN it belongs to. That way the receiving switch can properly process it. So in this nugget, we've taken a look at the world of routing and switching. In the world of routing, we had two primary functions. One was to learn what to do by either having directly connected streets or networks, having static routes configured, or by dynamically learning through a dynamic routing protocol. We also identified the process of what a router does when it receives a packet. It looks at its routing table, and then it makes a forwarding decision based on that routing table. There's different types of routing protocols, including IGPs, which are used within an organization. Examples of RIP are an example of a distance vector routing protocol. OSPF is an example of a link state routing protocol. And the EIGRP, Enhanced Interior Gateway Routing Protocol, is an example of a hybrid or an advanced distance vector routing protocol. To connect two different internet service providers together so they can share routes, they use Border Gateway Protocol, which is the only real example of an exterior gateway protocol that we use today. At layer 2, we deal with MAC addresses, layer 2 addresses. In the world of switching, a switch only forwards if, or I should say it forwards based on the destination layer 2 address. Switch doesn't bother forwarding a frame. If it knows where it belongs, it doesn't bother forwarding it to all other ports like a hub does. And on a switch, we have an individual collision domain, a separate collision domain on every single port. For broadcasts, however, all the other ports that are in the same VLAN are going to receive the broadcast domain. And if traffic needs to go down trunks, we're going to go ahead and tag that traffic with the additional layer 2.5 information of the VLAN that frame belongs to. Now, as far as other tidbits, why do I have that here? There were, in the objectives for the CompTIA, for section 1.4, they had routing and switching, and then they had a couple that were just off, I consider, tangent items. So I wanted to leave that for here and talk about that for a moment. Let's say we have a switch, and we have lots of devices connected to it. Maybe you have a router connected here, a PC connected here, and those guys are all assigned to VLAN 2, each of the ports. If we wanted to analyze the traffic, copy all the traffic that maybe is going out on port 2, or maybe in on this port, what we could do is we could tell the switch to copy all the data. I'll use a different color. Copy all the data to this port, and then we could plug in, for example, a protocol analyzer, which I've used in class a few times so far. And a protocol analyzer, if we're taking all the data on these ports and just making a copy, we're not stopping the traffic, we're just making a copy, we send it down here, then with a protocol analyzer, we can take a look at all the frames. See, a switch, normally, between the PC and the router, would not forward that traffic to any other port. So our protocol analyzer wouldn't be able to see it unless we have a special copy function. And so they call that special copy function several different names. One name is called port mirroring, mirroring, port mirroring, and sometimes it's called port monitoring. So that's how if we want to do protocol analysis, that's one way of doing it on a switched environment that otherwise wouldn't allow us to see that data. We have covered all the objectives in section 1.4 from the CompTIA Network Plus certification requirements. I hope this has been informative for you, and I'd like to thank you for viewing.